In this video, we're going to work example problems where we're given a function like this, and we want to find a power series representation for the function, along with the corresponding interval of convergence. Now, up to this point, the only way we've learned how to do this is by starting with this. You could call it like a base power series function, using this as a starting point. And all this is you can see it's the power series with the c sub centered at 0 with the c sub n just equal to 1 for all n. And what this is, you can see, is it's a geometric series with first term 1 and common ratio x. And so if this converges, we know when the absolute value of x is less than 1, and when it converges, we know the formula for for an infinite geometric series, it converges to the first term over 1 minus the common ratio. And so, but usually we have this formula here on the right-hand side, but it's flipped because the idea is we're looking at this as this function here is represented as a power series. And so what we're going to do is, for each of these functions that we're given, we're going to try and put the given function we have into a similar form as this, or we're going to think about if we differentiate this, and then we have to differentiate the power series, which we know how to do. Does that result in a form that we can work with to like a parallel form to the function we have? Or maybe if we could integrate this, would we get a form of a function that's similar to what we have? So that's the idea. Okay. So can we take this function and put it into a form that's similar to this, and therefore get a power series representation for this function? Yeah, we can do that. So first, we'll bring this 5 out away from the fraction. And we're going to do that because, remember, constants, you can always just bring outside of the summation. And so we want to make this a 1 up here because that's similar to this. Okay? So now what do we have? Well, okay, if you compare these two, so if you think about, we know that like a power series like this, as far as when it converges, we think about this as a function. So we'll say like this is g of x, since this is f of x. So it's a function, right? You input an x, as long as it's within the interval of convergence, you input an x and you get out a value. And this is the function here. This is the function for the series. And so what you can see, though, is that this here, what is this? This is g of 4x squared, not minus 4x squared. If we input 4x squared here, we get what? We get 1 over 1 minus 4x squared. Well, okay, but the whole idea is, forget about this. We want to, if we had g of 4x squared, what does that make this? This is what we want. Well, we're just going to replace x with 4x squared. So we've got 5 times, and then just sum from n is equal to 0 to infinity. And there you go. Right? That's f of x. That's this. Now, we could, that's technically we're done, but I mean, other than finding the interval of convergence, but we could try and write this in the cleanest, most descriptive form that we can. So maybe we'll say that, let's do this. We could consider bringing the 5 inside. I guess we could do that. So 5 times 4 to the n times x to the 2n. That is a power series representation of this function. That's pretty cool. Okay, but what's the interval of convergence? Well, not every power series is a geometric series. it's very close. They're very closely related. It's always has a common ratio no matter what, a power series, but technically it's not like every single power series is going to be a geometric series. And so you can't, what I'm saying is you can't always just go to the X term and treat that as a common ratio and just say the absolute value of that is less than 1. If it's not a technical geometric series, then you need to do the ratio test. But here, this would be a geometric series, because what makes something not a geometric series is that if so you can have a common ratio, but if the constants are changing with each end, then it's not technically a geometric series. Here, it's you pick an X and you've got whatever's inside here, and whatever's on the outside is the same for every term. So this is a geometric series. Therefore, we know for a geometric series, the criteria for convergence is that the absolute value of the common ratio needs to be less than 1. Okay, so we know that, so 4x squared is positive for all x, so we can just remove the absolute value. Okay, now here we've got a quadratic inequality, and we learn how to solve quadratic inequalities in algebra. What you do is you bring everything to one side with the other side equal to 0. And then you just like solve this as if it were equal to 0. Okay, so let's solve this quadratic as if it were equal to 0. So, okay, we would have 4x squared minus 1 is equal to 0. So we would actually go ahead and bring this back over here. X squared is equal to 1/4. Square root property. So x is equal to plus or minus 1/2. So, okay. So this, if we could have factored this, and we would get x is equal to 1/2, x is equal to minus 1/2. And so what we do is we draw a number line, and these 2 points are like boundary points. And we just check. So like this is, we could write this. This would factor as x minus 1/2, x plus 1/2 is less than 0. And then we'd have, that's x squared minus 1/4 is less than 0, right? But you would have, so okay, x squared, yeah, so with a 4 out front. That's what this factors as. So when is this less than 0? You can see the 1/2 and the minus 1/2 of the boundary points. So if x is less than minus 1/2, what happens? This is positive, this is positive. If x is greater than 1/2, this is positive, this is positive. So it's going to be, and then it's not at the endpoints either, because it's not less than or equal to. So it's in here, minus 1/2 to 1/2. Okay, but just checking for what we just solved that for when is the absolute value of 4x squared less than 1? That's when x is between minus 1/2 and 1/2. But that didn't tell us anything about the endpoints. So we've got the radius of convergence. It's 1, or no, it's 1/2. But what about the endpoints? So, okay, when x is equal to minus 1/2, what do we have? This is 5. So, okay, minus 1/2 squared is 1/4. So you've got 1 to the n. Is that right? Well, this is divergent, right? This is just 1. So we could bring the 5 in. The sum from n is equal to 0 to infinity of just 5. That's divergent. Okay, what about 1/2? So it's same thing, divergent. So this is the domain of this is minus 1/2 to 1/2, not including the endpoints. Okay, same process. Can we create like a parallel between these two? Because for all these problems, this is we're building off of this. So, all right, we can say that. Let's bring that 2 out front, and now we've got 3. Okay, that's an improvement. We've got the 1. The numerator is a 1, but now we need this to be a 1, the 3 to be a 1. So let's factor out a 3 here, and we've got, so we can do this. See? So, okay, comparing this to this. Yeah, that works, because again, if this is g of x, then this is g of x over 3. Not minus x over 3, x over 3. So f of x, we've got 2/3, and then g of x over 3. So that's like that. So, I mean, we could actually just leave it like that. Let's bring the 2/3 inside. So 2/3. There you go. That's a power series representation of this function. That's really cool. But we need the interval of convergence. And so this is also geometric. We can look here. This is geometric, right? With the first term 2/3. So for a geometric series, the absolute value of the common ratio needs to be less than 1. Okay, so here's another absolute value inequality. And if we think back from algebra, these are properties of absolute value inequalities. We could have done this with the quadratic, but there was kind of a separate section on quadratic inequalities. But in general, this is how you look at an absolute value inequality. We could have, the quadratic inequality procedure comes from this. But in general, for any inequality, if you have the absolute value of an expression, the variable expression is less than a constant number, where that constant number is greater than 0, then that's equivalent to this compound and inequality here. So the expression is less than the number, and it's greater than minus that number. So this is x over 3 is less than 1 and greater than minus 1. So let's multiply this entire inequality by positive 3, so we don't have to flip the inequality. And there we go. But when it comes to this only tells us about, this doesn't tell us about the endpoints, right? We know the radius of convergence is 3, and we know the interval of convergence, but we don't know the endpoints. So we have to evaluate the endpoints manually. So plugging in 3, we've got, this is 1 to the n. So just 1, this is divergent. Sum from n is equal to 0 to infinity of 2/3, that's divergent. Okay. Minus 3. This is going to be minus 1 to the n. This is also divergent. You're just oscillating. You're doing, this is 2/3. I think it would start at 2/3. Minus 2/3 plus 2/3 minus 2/3 plus 2/3. You might say, well, does this converge to 0? No, because like, okay, yeah, this is 0, but then this is 2/3. Then this is 0. You're just oscillating between 2/3 and 0. So this is divergent. So the interval is minus 3 to 3, not including the endpoints. Interval of convergence. We just represented this function as a power series, and we gave the domain is what we did. That's what the interval of convergence is. It's the domain of this is a function. This, like f of x is this and this. This is a function of x. This is the domain. Okay. Let's see if we can create like a parallel form here. All right. F of x is equal to 4 times, well, no, let's put the x term second. Okay, and so the idea is that this x can like be anything, right? It's really, we're trying to create the exact form for everything else but the variable, because like this is, we can input anything we want into this function. So okay, we need to get a 1 here, so we factor out a 3. So now we're going to write this as minus 2/3 x. And there we go. So this, you could see, is g of minus 2/3 x. Right? You agree that these two are equivalent. So, okay, that means f of x is equal to 4/3 times, and then you've got minus 2/3 x, like that. Okay, now, so we can try and write this in the simplest form that we can. If we think about 4 is 2 squared, so let's do this. We've got, so minus 1 to the n times 2 squared over 3 to the first times 2 to the n over 3 to the n times x to the n. So minus 1 to the n, and then you've got 2 to the n plus 2 over 3 to the n plus 1, x to the n. Yeah, there we go. So this is, we could do it like this. Okay, now the interval of convergence, you know, typically you would look at this and you would think that this is potentially not geometric, because, you know, you would think it's not just a single common ratio with with constant terms out front, but we know this simplifies to this. So now this is technically not geometric. I'm not sure what the definition would be, because you're oscillating between 1 and -1, right? But when you think about testing this for absolute convergence, you're testing a geometric series anyway. So it's going to be the case that, you know, you could take out the minus 1 to the n, then you take the absolute value of this series. It's going to be that this is going to converge when this is less than 1. The absolute value of this is less than 1. Okay, so properties of absolute value equations, that's just that. Multiply the entire inequality by 3. Now divide everything by 2. We don't have to flip anything. Okay, so there's the interval, but we need to test the endpoints. So when x is 3/2, we've got so 3/2, that's minus 1 to the n. That's going to diverge. You're just oscillating 4/3 minus 4/3. Okay. This is 1 to the n. That diverges 2. So this is, the interval is minus 3/2 to 3/2, not including the endpoints. Okay, this might seem intimidating, but what's really nice about, with these x terms, remember that x is not a function of n. So you can bring x's out of the summation. The only reason you can't do that like with this is because it's like the x is attached to the n. You can't bring n's out of the summation. So what we're going to do is we're going to start by just bringing this x squared away from this, and then we're left with 1 over, and let's bring the 16 first, or x to the 4th. Right, so we can potentially try and match these two up, but we can bring the x squared out of the summation, at least temporarily. So, okay, we need to make a 1 here, so we've got 16, and then 1 plus, okay, so this is x squared, and then you've got 1 minus x. Okay, so, if this is g of x, then this is g of minus x to the 4th over 16. So we've got that f of x is equal to x squared over 16, and then just substitute in minus x to the 4th over 16 here. And there we go. But to determine the interval of convergence and all that, we need to bring this x back in and do some simplification. But yeah, I mean, that's the idea. This x squared here, now that we can just bring this back in, right? There's no n attached to this. X is not a function of n. This summation is all about, it's associated with the n's. So this is just a constant. It just depends on, it's a constant in the sense that once you pick an x, this becomes a constant, right? It's not a function of n. Okay, so let's x squared over, let's do this, 2 to the 4th. Let's take our time with this. So we've got minus 1 to the n, and then x to the 4n over 16 to the n. Okay. So minus 1 to the n. So x squared over 2 to the 4th times, now this is 2 to the 4n. Okay. So we've got, let's do this. So 2 to the 4n plus 4, and then x to the 4n plus 2. Yeah, there we go. Okay. So that's the form we'll put it in. All right, but what's the interval of convergence? Now, this is a little different because we don't we can't come back to any point and clearly see that it's a geometric series. It might be, but you can't just say, oh, well, it's when the absolute value of x is less than 1, because this is a common ratio. That is true. There is a common ratio with every single term, so it's very similar to a geometric series, but this is technically, it's probably not a geometric series. The coefficients are changing. So we need to do another test. We're going to do the ratio test. So, okay. We can just get rid of that minus 1 to the n, and we've got, so x to the 4, so we're substituting n plus 1 for n. So 4 times n plus 1 plus 2 is what? That's 4n plus 6. So x to the 4n plus 6, and then 2 to the 4n plus 4. So 4n plus 4. Okay, so 2 to the 4n plus 8 times, then we've got 2 to the 4n plus 4 over x. Okay, so this is x to the 4n times x to the 6th, and then 2 to the 4n times 2 to the 8th, and then 2 to the 4n times 2 to the 4th, x to the 4n times x squared. So 2 to the 4n, those cancel. This, okay. So this is what? X to the 4th over 2 to the 4th. And with the ratio test, the requirement for convergence is that this is less than 1. So we need to solve this inequality. So multiply both sides by 2 to the 4th. Okay, and a quadratic or polynomial inequality, you just solve it. You set this equal, and you solve for all real solutions. That's what you're doing. But you actually do want to factor it, because you want to bring everything to one side and factor it, because you can see where the boundaries are. But that's actually, you would know where the boundaries are once you solve it. So, because that's the idea. With a polynomial or a quadratic inequality, you can think about bringing everything to one side and factoring it, and that's how you're going to see what's less, like when it's less than 0 or greater than 0. So if we, again, we do this in algebra, polynomial and quadratic inequalities. So we want to solve x to the 4th is less than 2 to the 4th. So we say we bring 2 to the 4th to this side. But now let's factor this. So that's x squared minus 2 squared. So you've got x squared minus 2 squared is 4. Well, let's do this. X squared plus 4, x squared minus 4. Okay. So this x squared minus 4 factors. Right? So now where it equals 0, we solve for all real solutions, or where this doesn't exist, but this exists everywhere. So it's at 2 and minus 2. That's where this sign can change. So this is always positive. So when x is less than minus 2, this is negative, this is negative, this is positive. When x is greater than 2, these two are positive, so it's going to be in between is where this is going to be satisfied, but not including minus 2 and 2. So, yeah, because the ratio test doesn't tell us about the boundaries. So, yeah, minus 2 to 2. Okay, but we need to check the endpoints. So, at 2, we've got... All right. You've got, so, times 2 to the 4n plus 2. So let's do this. 2 to the 4n times 2 squared. And then here you've got 2 to the 4n times 2 to the 4th. So this is just 1 over 4. That's divergent. Okay, and we can see that that was 2. Okay, this might be, let's see what happens. It's going to be the same thing. So minus 1 to the n, and then we've got, you never know, maybe it's different. It'll converge. So you've got, what happens is you've got minus 2 to the 4n plus 2. So you can take out a minus 1 to the 4n plus 2. Combine those, you get minus 1 to the 5n plus 2. So it's going to be alternating. And so 5n plus 2 is that when n is equal to 0, that turns minus 1 into a positive. So it's just, you can just leave minus 1 to the n. Same thing. You just have to see, you combine them, you get minus 1 to the 5n plus 2. Does that make every even term positive or odd, or every odd term positive or odd? Because with alternating, you could just put either minus 1 to the n or minus 1 to the n plus 1, you know? Okay, so now we're left with just this. It's going to be the 1/4, right? We're left with what we had before. 2 to the 4n plus 2 over 2 to the 4n plus 4. So it's divergent. So this is minus 2 to 2. Okay, so let's bring this x out, and then we'll have 1 plus 2x squared over 1. So we can write this as 1 minus 2x squared, and all that under 1. So this here is, if this is g of x, this is g of minus 2x squared. So we've got that f of x is equal to x times, and then like that. Okay, but let's bring that x back in. We've got minus 2 to the n times x to the 2n times x to the first. So this is minus 1, 2 to the n times x to the 2n. Okay, let's see. 2 to the n times x to the 2n plus 1. Yeah, there we go. So all right, now we can't, it looks like this is not geometric. So let's just go ahead and do the ratio test. So the All right, to get rid of this. So we've got 2 to the n plus 1 is 2 to the n times 2. And then x to the 2n plus 1. So 2 times n plus 1 is 2n plus 2 plus 1, 2n plus 3. So let's do this. X to the 2n times x cubed all over. So then 2 to the n times x to the 2n times x to the first. So these cancel. We're left with 2x squared. This needs to be less than 1. So quadratic inequality. X squared is less than 1/2. So x squared minus 1/2 is less than 0. We could factor this. So x plus 1/4, x minus 1/4 is less than 0. So that's the boundary points, and we can see that if it's x is going to be between 1/4 and minus 1/4 when this is going to be less than 0. Okay, so now let's check the endpoints. So f of 1/4, let's come here. So all right, 1/4, okay, minus 1 to the n times 2 to the n times, you can have 1 over then 4 to the 2n times 4, because that's 4 to the 2n plus 1, right? But then 4 to the 2n, that's 2 to the 4n. Well, okay, no, let's do this. 4 to the 2n plus 1 is 2 to the 2n plus 2. Is 2 to the 4n plus 2. So 2 to the 4n times 2 squared. Right, so let me not rush this. So 4 to the 2n plus 1, that's 2 squared to the 2n plus 1, that's 2 to the 4n plus 2. So 2 to the 4n times 2 squared. So, okay. That's 2 to the 3n times 2 squared. So it's 2 to the 3n plus 2. Okay, now we can write it this way. You got minus 1 to the n, and then you can just bring this exponent, we could do this. Right? Well, this is a geometric series. Well, it's not because it's alternating, but we could do the test for absolute convergence, and the absolute value of this series is a geometric series with the common ratio less than 1. So positive, it's going to converge at positive 1/4. All right. Now, what about at negative 1/4? So, okay, we're going to have, let's just come to the side and do this real quick. So let's make sure, I want to make sure, okay. So the 1/4, let me check the 1/4, the positive 1/4 again. So 2 to the n times, you have 1 over 4 to the 2n plus 1. That's 2 to the n times 2 to the 4n plus 2. So 2 to the n times 2 to the 4n times 2 squared. That's 1 over 2 to the 3n plus 2. That's 1/2 to the 3n plus 2, and then everything else is just minus 1 to the n. Absolute value, that's a geometric, yeah, okay. So now we've got, so let's just focus here. We have 2 to the n, and then we're going to have 4 to the 2n plus 1, so it's going to be 2 to the 4n times 2 squared again, but then minus 1 to the 2n plus 1. So minus 1 to the 2n plus 1 times minus 1 to the n, that's going to be minus 1 to the 3n plus 1. If we think about what that means, at n is equal to 0, the power is odd. So this is just making, like, the first term is going to be odd, second term even, third term odd, fourth term even. And so we just need to, we can write this as minus 1 to the n plus 1, same thing. That's what that turns into. So let's do that. Okay. So now we can just focus on, we can get rid of this. Well, we just did this. This is going to be 1 over 2 to the 3n plus 2. This is just 1/2 to the 3n plus 2. That's convergent. It's absolutely convergent. So this here, this is actually convergent at the endpoints. Okay, last problem. What we want to do here is split this up. So we can do polynomial long division here to split this up. So you can split it up however you want into two separate fractions. So, okay, x divided by x is 1. So minus 1 minus 2 is minus 3. So this is going to be 1 minus, is that right? So x plus 2 over x plus 2. If you write this as x plus 2 over x plus 2, you get x plus 2 minus 3 is x minus 1 over x plus 2. Yeah. So with that, we want to write this as a summation. So what we've got is this f of x is 1 minus 3 times this is 1 minus 3 times, factor out the 2, 1 plus, so we've got 1 minus 3/2 times, and then 1 minus, there we go. It's pretty cool, right? We've gotten all the way to this point, and we haven't changed this function. Okay, if we say that this is like g of x, then this is g of minus x over 2. So the f of x is 1 minus 3/2, sum from n is equal to 0 to infinity, and then substitute minus x over 2, like that. Okay, and so this is geometric, so we can solve for when is the absolute value. Well, okay, so let's do, so minus 1 to the n, like that. Okay, now you can play with this, and like, so the textbook might change the n to n is equal to 1, and it'll simplify this a little bit more, and maybe you could try and make this a whole number, and this a whole number as well, like it already is. But so, I mean, yeah, let's see if we can. The textbook has it in a different form. Well, let's get the interval of convergence here. So if we think about the absolute, this is geometric from the standpoint of if we take we evaluate for absolute convergence, right? It turns into geometric. So this is convergent when this is less than 1. So absolute value equation, multiply everything by 2. Okay, so from -2 to 2, and then we can go ahead and look at the endpoints. So when x is equal to 2, what do we have? So 1 minus and then 1 to the n. This is divergent. This should be, we're doing 2. Okay, f of -2, you get, okay, -1 to the n times -1 to the n is, you could look at -1 to the 2n, and so -1 squared is 1, or you could just say -1 times 1 to the n. So it's just this. That's also divergent. So, okay, the interval is -2 to 2, not including the endpoints. But let's see if we can get what the book, the answer that the book says. So they have this starting at n is equal to 1. So, you could put this in whatever form you want. So if we did that, what would happen? Well, okay. If we look here, when n is equal to 0, this is positive. So the first term is going to be positive. Like, we're not changing the series. When we change this to n is equal to 1, we're not changing the series. We want an equivalent series. So the first term is going to be positive, and it's going to oscillate from there. So we want this, we could do n plus 1 or n minus 1, whatever. I guess n minus 1, let's do that. N minus 1. So when n is equal to 1, you've got -1 to the 0, and then it oscillates from there. Okay. And then it's actually, that's how this is going to be n minus 1 as well. Because here, the first term, you have n is equal to 0, and that's what we're changing it to. The first term, n is equal to 0. Second term, n is equal to 1. Third term, n is equal to 2. Here, first term, it's the n is equal to 0. Second term, n is equal to 1. So now the textbook, then they bring in this. So -1. Where in the world is the textbook getting this? Oh, okay. No, I see. They did this. Okay, they changed this to starting at n is equal to 1 by doing this. I don't know why you would do this, but so 1 minus, when n is equal to 0, what do you have? The first term, if we bring the 3/2 inside, first term is 3/2. Okay, now you have to be careful here. You might think, well, just put plus and then just put the summation. But okay, let's do that. So we've got 3/2, and now we're starting at 1. And nothing's changed because we took out that first term. Right? We had 1 minus this, and the only thing we did was just take out the first term. And then now we're just writing this exact same summation, but starting at 1. That's the only difference. And you think, okay, this is it, right? This is these two are equal. No, this would be wrong, because okay, we know that we want this next term to be positive, right? Well, okay, but n is equal to 1. It's going to come out. What's going to come out of this is a negative term, the first term at least. So we need to make this negative. And then now everything else will continue on as normal. So all of this is very intuitive. You just have to be careful. Okay, so 1 minus 3/2 is -1/2. Now what they did next is they brought this 3/2 inside the summation. So you've got 3x to the n over 2 times 2 to the n. And so what we've got is minus 1/2 and this goes from minus 2 to 2, not including the endpoints. Now, you didn't have to go through all these extra steps to put it into this form that the textbook put it into, but I'm glad we did that. That's just some good practice of rearranging and manipulating series.